Okay, I think I got it now. So important news of the week is the announcement of the Universal Chiplet Interconnect. Essentially, many of the major players in industry, including Intel, ARM, AMD, and pretty much all the cloud providers have agreed on a universal interface for attaching chiplets. I remember when I talked about the chiplets just 2 weeks ago, I said that everybody had their own interface and you cannot take one company's chiplet and attach it to another company's chiplet, except for rare examples of some other people attaching things to AIB, Intel's AIB. This is an evolution of AIB, and I believe it is a significant development because the standard is open. Open meaning that anybody could put an interface and attach their chiplet on the other side. It is easy to imagine that relatively quickly there will be some of these major providers will offer a big processor SoC that will have a UCI port on it. There may be something attached to that with UCI port, but you can easily pop that out and put your own thing in. Why do you guys think this is important? Any opinions from the quiet crowd? Industry tends to start closed, and we have seen that many times. So they develop something that works for themselves, and then they hold both sides of the interface closely because they believe they can win some market share by doing that. And then they get choked. And the way to break out for that is by opening up the interfaces. I think very similar, this shares in spirit a lot of what you'll find in CXL. CXL is Chip Express link or something like that. That is an open standard that has been used typically in clouds and big systems for connecting to storage and networking and so on. It was late, but Intel decided to open it up. Because it was opened, everybody else adopted it. There were other interconnecting interfaces out there, but they didn't do well or were not as widely adopted because they were closed. You had to have something, in order to have that interconnect, something, there was a string attached. You had to have an ARM thingy in there. So we'll see how this plays out. This is really, really important. I mean, you can see who is signed up early on. Cloud people, hyperscalers, because they see an opportunity there. But I think it will have a much broader adoption, and it will affect the way how perhaps you do your research, or perhaps how business in this field develops. There will be significant opportunities. You can just imagine. One of the things that I hinted 2 weeks ago or 3 weeks ago is this thing that the NRE is expensive here, and a lot of NRE goes into purchased black box IP, integrating it, verifying it, to add a little bit of our stuff to it. That is a value proposition and a differentiator. How about instead of that, then we know many people where there is a chip where there is $1,000 worth of NRE in each one of these chips that are sold. I mean, if the volume is not high, if it is only like tens of thousands or hundreds of thousands of units, there is a lot of NRE in there in each chip sold. All the entire telecom infrastructure is like that. Now, instead of doing that, you can just buy chip, perhaps cheaper, and attach your differentiated IP to it. Ken, you are.
I get the protocol, like I mean that you standard is kind of laid out, the information about what, but it feels like they didn't express anything about the electrical standard or like interposer or substrate. So how, I mean, ultimately are you going to bridge that, because that is still proprietary,
Excellent point. So the standard is open, but the implementation is not free, because the implementation has to be tied to a technology. So we'll see. I mean, there is a similarity between RISC-V and that. RISC-V ISA is free, but there are open cores and not open cores. I believe Intel said that they're going to provide, if you're an Intel process, you get this piece of IP, because it is obvious they're going to sell you a processor that has that, and their value is in the processor, in the fab, and they really don't. They're not showing any interest in monetizing that IP. Someone else might try to do that, and there is clearly a business opportunity. And I bet you there are a couple of companies that have jumped on that, providing that kind of an IP for global foundries, plethora of TSMC processes and so on. One can imagine coming up with a generator or something like that in bag or and so on, and trying to get a good chunk of a market. I mean, I bet you there is a company looking at that right now. But I think there will be some forms of open solutions. Yes, this is going to be tied also to the interposer design, the substrate design. And these interposers are not going to be trivial. But if you are going to have a Xeon on the other side, or even a laptop class or processor, this is not a cheapo thing. This is not for people who are trying to make a $2 chip. It is for electronic systems that cost a few hundreds to thousands of dollars, and there are plenty of those. Okay. All right, let's move on. We've talked about standard cell architectures, and we've seen the architecture of how it looks like around 7 nanometer node. 5 nanometer nodes are similar, but there is a variety of those. There are many of them out there, and things change. The architecture of a standard cell looked different in 130 nanometers, then it looked in 20 nanometers, and certainly looks different in 7 nanometers, and it is going to change again when we see nanosheet-based transistors. By the way, that's yet another opportunity. If you got good ideas, go for it. There is a market. How much does a standard cell library cost at the moment? If you want to buy a standard cell library, how much do you have to pay? Any wild ideas?
Millions?
It's more than $1 million. I mean, even the smaller ones are more than $1 million. Can be 2 or something like that. You see that as a problem. Someone else sees that as a business opportunity, and trying to figure this out, to do it more efficiently, because it involves a lot of labor in characterizing it, laying out or something like that. I mean, I bet you ML can figure out this standard cell layouts and so on. It's a lot less complicated than some other things. Again, I'm just trying this out as an opportunity out there. We have talked about characterization of a delay, and we would like to dive into that and see, what do we do with that. So let's talk a little bit about timing. We have seen timing before, and I will, the beginning of this lecture will be a reminder, and then we're going to dive, add more details to that. So in the typical clock system, there is something that comes in as a system clock, typically low frequency, generated by crystal from off chip. So there may be some kind of an oscillator over here that is hooked up to a crystal. Let's see if my inking is going to work. There is a no. So there is a crystal here, and there is an oscillator that provides this clock. This is typically low frequency. What comes in from, depending on the application, from tens of kilohertz. Typically, if it is a PC, maybe tens of megahertz. There is a one thing that some of our students are really surprised, and especially when we try to go and build something out there. There is a whole bunch of different crystals out there. And you can buy them for pretty much any frequency you want, but you'll find out that like 32 megahertz crystals or 32 kilohertz crystals are dramatically cheaper, or 40 megahertz in particular, are dramatically cheaper than if you want to buy, 50 megahertz crystal or 30 megahertz crystal. So some of them are incredibly cheap. Why? Anybody has any idea? Why are some of them, $5 and some of them are 10 cents? And they're like the similar frequency. They look exactly the same, but some of them are 15 cents, some of them are $5. Any idea? Because certain frequencies have been used in, for example, PCs, or I don't know, Bluetooth or something like that, and they became cheap. Those that are not as, that they're more exotic, they're expensive because they're not made in enormous volumes. So it's one thing, lessons learned over there. In order for something to be used in a Bluetooth type of a thingy, or anywhere on a keychain USB, all that has to be really cheap. Most people will go, all electronic systems are going to be based on those, unless you really need something that has a special frequency, and then you have to pay the price. So we'll take that frequency and we will multiply it and divide it. We'll talk about PLLs later on in the class, but essentially what you'll find out, you have this, FSys will be multiplied by N and divided by M to produce the F global, which is the frequency over here. That is generally going to be distributed throughout the chip, and you'll find out that those are the frequencies that typically run at few hundreds of megahertz. There may be additional PLLs. There is an option to have another PLL supplying the blocks, or these clocks may just be derived from the global clock. Yes.
What does PLL stand for?
PLL is a phase lock loop. And I'll talk more about phase lock loops as I, towards the end of the class. Now, either me or Vladimir will cover it. In general, there will be many blocks. You can think of these blocks as microprocessor cores, or on-core, or cache, or peripherals, and so on. And each one of them will have their own clock. In this example, they all have the same clock frequency, but by using different PLLs, or perhaps DLLs, as we'll see later, they can get their own frequencies. Generally, every system nowadays is going to have some amount of clock gating. They have to have clock gating in order to save power, because you're not always going to be, most of the chips nowadays are power limited, or all of them are power limited. If you look at the iPhone processor, application processor, you know that you cannot use everything that is on it all the time. There are many reports where people have figured out that you can, they can burn something like 6 watts instantaneously out of that. Well, it's gonna kill the battery, and it's not gonna be pleasant to have in your pocket. And on the average, the power consumption has to be much less. In most of the time, it is regulated by power gating or clock gating. Now, since we have so many blocks, there will be differences in clocks by the time this clock goes through a clock tree over here. And these clock trees have many. It's just stopped. I just got brave and decided to continue to try inking, and it just does not work. Wrong. Okay, I'll minimize my usage of ink, and I'll try again towards the end of the. Okay, so in general, the clock that is seen at all the leaf nodes between different cores and different elements on the SoC is going to be slightly different. There will be clock non-idealities. These clock non-idealities, as we have seen, are typically characterized as clock skew, which is a spatial variation in temporally equivalent clock edges, meaning the same clock edge that corresponds to the same event from the global clock will be arriving at different times to different nodes in the chip. There will be jitter, which is a temporal variation in consecutive edges of the clock signal, meaning that the period of the clock will be changing cycle to cycle. And it can be characterized as a short-term jitter, which will be mostly caring about the long-term jitter that matters mostly to interfaces. And there may be a variation in pulse width that is important for level-sensitive clocking. Does not affect flip-flops. Here is a picture of clock skew and jitter. Clock skew is a spatial variation to different clocks that are reaching two different nodes, may be arriving at a different time. So that is the skew. On the average, they're going to arrive at a different time. Now, temporally, both of these edges are going to be varying because of variations in the in either the clock source or the clock tree. In the past, majority of the jitter, a long time ago, majority of the jitter was associated with a clock source, associated with the noise from the PLL, essentially. That means that clock jitter affected all the clock sinks, all the nodes that are being clocked equally. And that was the argument that I've mentioned before in 151, is that it really did not affect something. What it did not affect? If it is all associated with clock source. it did not affect. So when do we care about if it is the same edge, right? So things that are if jitter affects two consecutive edges, it will definitely affect two consecutive edges. If it is associated with the clock source, then it will go into a setup time, minimum cycle time calculation. But hold time is always associated with the same clock edge. So all hold time violations, all race conditions are associated with the same clock edge. So any jitter that is associated with the clock source can be dropped out. Now, in modern systems, things have changed. Majority of the jitter now comes from the clock distribution network, not the clock source. There's still some component, PLLs are not noisy, and they do produce some amount of jitter, but majority of that now comes from the clock distribution network. Because clock distribution network is so big, and there are so many things that are happening in there, like supply variations and so on, that it affects jitter. So a component of a jitter has to be accounted for in both setup time and hold time violations calculations. However, whenever you do that calculation, I mean, in class and research projects, we put a lump sum in both cases, very conservatively. If you're designing a product, you'll find out that there is a very careful attempt to try to quantify how much of it is in there. Why do we have clock uncertainties? Explaining the sources of skew and jitter. They can be coming from clock generation. And different devices on a chip may have different thresholds, different performance. There are variations in the interconnect. And what you'll find out is variations in the interconnect length between clock buffers and flip-flops that are receiving them can be systematic or can be random. Similarly, many things can be systematic or random. We are going to talk about systematic and random variations in next lecture. But often when we do box tree synthesis, and you guys have seen that, we put some amount of budget to how close do we want to have these clock edges, to how small of a skew do we want to have. That is essentially that skew is because of the variations in the interconnect and perhaps variations in the capacitance. Why don't we go for zero skew? Why do we allow for that systematic skew to exist? Has anybody tried in your lab to go for a zero skew and see what happens? I mean, even in a lab with a fake process, this is going to go to infinity. The computer will try to achieve a very small skew, but that is something that's infeasible in very large, reasonably large systems. So we have to put a reasonable, we need to accept some amount of systematic skew. And then on top of that, there will be a random skew that will be there. Also, it does not make sense to try to go for a zero systematic skew because it is impossible to account for everything over here. We'll mention that later. There'll be some coupling with adjacent lines. It's hard to predict. I mean, it's going to be also data dependent. Your capacitive load will depend whether there is a 0 or 1 on the data input. There is a slight variation, but it varies, and so on. Miller effects and all that kind of stuff that we've been talking about will affect the capacitance a bit, and we're not going to have the zero skew and zero jitter. Temperature on chip is going to vary, and therefore the propagation delay will vary as well. We have talked about this before, and do I dare to put some ink on this again? But we have seen this in 151, so I'll go relatively quickly. There is one significant timing arc in flip-flops. It is a timing arc that goes from clock input to the output queue. there are two important clock constraints associated with the flip-flop, which are the setup time and the hold time. We have seen all this before. But in general, the way how flip-flop works is the data arrives to its input and waits for the clock to show up. When the clock shows up at its input, typically on the rising edge of a clock, the data will be transferred to the output after clock to output delay. Now, flip-flop is you can view it as an analog circuit, as a sampling circuit that needs to decide whether that input is a 0 or 1. It cannot be transitioning from 0 to 1 or from 1 to 0 when the clock edge is rising, because it won't be able to figure out whether it's a 0 or 1. So the time that it is required for it to be stable before the rising edge of the clock is called the setup time. The time that it is required to be stable after the rising edge of the clock is the hold time. By definition, setup time before the rising edge of a clock is positive, hold time after the rising edge of a clock is also positive. Because of this definition, it will also happen that most standard cell hold times will have negative values, as you might have seen. Now, latch is a little harder to handle. Latch has two different kinds of parameters, or two different timing arcs associated with it. It has this thing it does not even want to try. I just tried touching it and it froze.
Does it help to just use a annotation?
I think I'm going to try to do that, although
Or maybe another way around it is to load the PowerPoint slides to Google Slides.
Yes. Let's try this. So there are two timing arcs in here. One is T D to Q. The other one is T clock to Q. You know what happened here? It will not do it. There are two timing arcs, and by the way, so it just basically means we are done with zone. there is no reason that the campus says that instruction is in person, therefore it's person. It was a convenience for those who couldn't make it, but no more. Sorry guys that are used to being on Zoom. So I'll continue investigating, but for now, anyways, the next lecture is a quiz, so it is in person. So there are two timing arcs. There is a timing arc associated with D to Q, and a timing arc associated with clock to Q. If data arrives to a transparent latch, it goes through after D to Q delay. If it arrives to a non-transparent latch, it waits for the latch to become transparent to be able to propagate through the latch after the clock to output delay. There are two types of latches, and what I'm showing here is a transparent high latch. There is typically a transparent low latch used in the same system. Transparent high latch is transparent when clock is equal to high, is high. So clock to output delay will be associated with the rising edge of the clock. Essentially, data arrives to a non-transparent latch when the data is, when the clock is low, waits for the clock to go high, therefore the clock to Q delay is associated with the rising edge of the clock. PD to Q is simply looks like a combinational logic delay. The clock has no effect. Data arrives to a transparent latch, just goes to a transparent. However, the really important thing to remember here is that setup times and hold times are associated with the edge of the clock that where the flip-flop or where the latch goes from transparent state to a non-transparent state. Why? Because that's when it needs to decide whether it should keep A0 or A1 for the remainder of the clock period. So that's where it has to make a decision. If you're an analog person, that is where it needs to sample the input data. So setup and hold times are associated here with the transparent high latch with the falling edge of the clock. Clock to Q delay is associated with the rising edge of the clock. By the way, this is whenever we have a pairing question that has to do with latches, 1 out of 10 students will get choked on wrong edge of the clock, trying to figure out where the setup and hold times are. Don't be one of those. In a very quick illustration here, this is from Hamid Portoviz, and I should have linked that book chapter, and I'll link it today. The book, many of really good, crisp description of flip-flop and latch-based timing is in the book chapter in that Chandrakasan edited book. I'll link it today. Super helpful over there. This is an illustration from over there, showing in one picture the constraints associated with both the long path and the short path. The long path constraint is the path that constrains the minimum clock cycle that we can apply to a particular digital system. So essentially, maximum amount of logic has to be less than the effective cycle that we are dealing with, which is the nominal cycle time minus the skew minus the jitter minus setup time and clock to Q, because that is the overhead that is associated with having a flip-flop in the system. So this is a characteristic of a flip-flop. It's setup time and clock to output delay. And we'll see in the next lecture that there may be different flip-flop designs. This is a property of the clock network. the difference between the cycle time and the maximum delay through the system is the margin, and we have seen that. In general, the job of a digital system designer is to manage the amount of margin versus budgeting of these things, jitter and skew. On the other hand, the amount of logic that we have has to be long enough to avoid any hold-time violations. So the amount that we have to be able to tolerate is the difference between the hold time and clock to output delay, with skew added on top of that, because the minimum delay in the logic is equal to the clock to output delay plus the hold time, and has to be greater than I said this wrong. This clock to output delay plus the minimum amount of logic has to be greater than the hold time plus the skew. In most systems, with most undersell libraries, this is really easy to meet because the hold time is negative by design of a flip-flop. We'll see why is that in a bit. Now, these equations look like they're deterministic, but there is a lot of probabilistic stuff that goes in there and budgeting. In general, and we'll revisit this picture a few times later, the way how timing tools look at this is by trying to compare the clock arrival times with data arrival times. So there will be some latest amount of clock arrival time that will go into the longest path calculation, and there will be the earliest clock arrival time for the next cycle that corresponds to the cycle being shortened by some amount of jitter. If we look into that, we would like to compare that with a time when it is legal for data to arrive. So the data can legally arrive after the whole time elapses, which is what we're going to call early required arrival time. And then when we add the setup time, we can annotate here what is the late required arrival time. So data can legally switch anywhere in between early and late required arrival time. You can switch once or multiple times. But these zones are the zones where you cannot switch. Now, when you time your circuit, when you do the timing analysis, you will actually annotate the actual arrival times of data. So those are going to be red. And you will compare the actual arrival times with the required arrival times, and you'll find out what is the slack. You will have two types of slack in there, the early slack and the late slack. When we're designing research chips, what do we care about? Which slack are we more concerned about? So say you design your fancy processor to run at 1 gigahertz, but it runs at 900 megahertz. Is that the end of the world? Now you write a paper about your 900 megahertz processor, and nobody ever knows that you want it to be 1 gigahertz processor. What happens if you have a whole time violation? It's bad. I mean, you can, nothing works. I mean, If you look at Sky 130 tape outs and drama that is unfolding over there, because they, this is the second tape out where the company that put together the harness around managed to insert whole time violations in it. And, so there are, it's ridiculous. But so what do you do when you have a whole time violation in your chip? I mean, okay, so he's, Ken is suggesting some, but but your option number one is you can cry. What's after you're done crying? And how 6 months of your life have been wasted. What is your next step after you're done with that? You go back from the lab and you realize you have a whole time violation. What do you do then?
Use some redundant logic.
But that's very advanced. That's what Intel does. So before that, we're talking about our research chip. By the way, there are so many chips in BWRC that have whole time value. Every year we have one or somebody, typically analog person. The last thing that they're doing is scan chain. They put in a scan chain, and a scan chain has a whole time violation done 24 hours before the tape out. Nothing works. Nothing can be configured as a result, or some parts can be configured, some other not configured. So what do you do then? Oh, you try to find out how bad is your whole time violation. If it is really marginal, you try to find another chip, and maybe you have some luck. The process queue has gotten you to do that. I mean, that is what people are suggesting on that Skywalker tape out. We'll try another chip. We find out that about 40% of chips you can get it to work, some bits to work. You can try operating at different supply voltages, because stacks have different sensitivities. All clock buffers are typically single stack. Logic can have multiple stacks, and there is different supply sensitivity, and so on. So there is some hope. But if you have a gross whole time violation, like nanoseconds, what ePablo said on the MPW1, then there is nothing you can do. You can only cry and tape out again. All right. So after that long spiel, what do we do in research chips? We had this more. And here, whatever happens, fine. What happens by, why do people don't pad this more with products? Why don't everybody just pad the whole time and don't worry about that? Because that increases the amount of logic that is in there, bloats the chip, increases the power dissipation, and is in general no good. But if you're an analog person and doing this on on your scan chain, just add it. Don't do it. Don't be skimpy. Question? No question. All right. Latch timing is a little more complex. So we don't cover it in undergrad classes, but I'll cover it briefly here, although it can be very, very hairy. Pretty much all digital systems, in 99 or more % of cases, will use flip-flop-based timing, but you will still see some amount of latch-based timing in some critical systems. Typically, interfaces will have latch-based latches, and the reason for that is because you can get more performance. But they're a lot hairier to get them to analyze them and get them to work cleanly. So we talked about this. When data arrives to a transparent latch is so-called a soft barrier. It just proceeds through combinational logic. When data arrives to a non-transparent latch, it has to wait and be relaunched on the rising edge of the clock. In order to sequence through flip-flops, we simply divide up the logic with the flip-flops and move it by applying consecutive clock edges. When sequencing data with latches, it is more squishy. The data does not necessarily stop at the latch. The timing part does not end there. The data may or may not go through that latch depending on the state of the latch. So there are two strategies that you will see out there. One, extremely risky, up on top, and done in a very limited set of cases nowadays, is single phase, single latch clocking. Why does this not work? In general, if we take it out of the box, why does this not nominate? It does not work out of the box. Assume having a clock with roughly 50% duty cycle. In order not to have a race condition, a whole time violation here, what is the minimum amount of logic that we need to fit into each path that we have each time? I mean, data can get launched on the rising edge of a clock and can just simply, if there is not much of a logic in here, it can race through all the latches downstream. If that was not your intention, that's a race condition. So how much logic do I have to have in every path? About or whatever is worth about half a cycle, give or take clock to output delay and the whole time. So that's a lot of logic. People have done systems like these, and you will see ideas of wave pipelining and so on associated with that. But it is not practical. I mean, if you said people are skimpy about padding short paths too much, padding the paths to have a half of a clock cycle worth of logic is way too much. So how do we do this? Here is an idea, and we have seen that actually done in many high performance systems. How about I distribute a clock like this? Will that work? Then my amount of logic just has to be longer than this. I just distribute glitches, and ideally I can just make it a really short glitch. So it's transparent for a short amount of time and just goes. What's the problem with this idea? Control my clock really well. What happens if I try to distribute this through an RC network that corresponds to, that's essentially a model of our clock distribution network. It's going to get filtered, right? I mean, I put this into something that looks like an RC network, and I get that. Is that good? I mean, it won't be attenuated. This one will be attenuated as well, but this one will be nicely filtered, right? Has higher frequency components in there. But generally, this is not a good idea. So what do we do instead? How do people do this instead? We'll see it in the next lecture. Instead of using they will distribute 50% duty cycle clock, and then they will have a glitch generator that essentially fires a latch. So this is clock that has a 50% duty cycle, and then we have a glitch generator that fires a latch. AMD has been building their processors for a long time that way, and others have done it too. The other strategy is to use alternate phase clocking. So you will have 2 phases of opposite phase clocks in all times. Those would have been non-overlapping clocks. So CLK1 would be like that. And CLK2 would be like this. They would never be transparent at the same time, assuming that both of these latches are transparent high. So there is no way for logic to traverse more than 2 latches. So this is a 2-phase non-overlapping clocking. Has been used in digital systems long time ago. It was a dominant way of clocking back, say, in the 80s. IBM used it in all their mainframe products. But that is wasteful. Why? Because in most cases during this dead time, non-overlap time, nothing will be happening. It is really hard to utilize it. It's also hard to control these non-overlapping clocks. So people walked away from that. What we will find out here is that clock 1 and clock 2 are opposite phases of the same clock, and we worked with that. And this is how it works. In general, then instead of using 2 different types of light, 2 different identical clocks, we'll use 2 different types of latches: transparent high and transparent low. So the one that does not have a bubble is transparent high. The one that has a bubble is transparent low. We'll feed the same clock to them, clock 1 and clock 2. They may have some different skews, but in general, it is coming from the same distribution. Now the question here is, what are the constraints for my CLH and CLL? And there is something interesting, there is a hint in here how the timing analysis goes. The H here means that this is the logic that is associated with the high period of the clock. L is the amount of logic that is associated for timing purposes with the low period of the clock, or low part of the clock. It's just combination logic, it's standard combination logic, but for timing purposes, we're expecting that CLH will be executed, will be evaluated during this time when the clock is high, and most of the propagation delay associated with CLL will be associated with the low part of the clock. How much time do we have to evaluate CLL and CLH? So if I try to time from some point here, say that this started evaluating when the latch was transparent. In general, latch-based systems are intended to operate with transparent latches. Why? Because it would be wasteful to time it in a way that the data in a critical path arrives to a non-transparent latch and then has to wait for the latch to become transparent. It's wasteful. I mean, you have just put a margin in it. The idea here is to operate like not Berkeley City traffic lights, but like Franklin Street in San Francisco. If you're going at the right pace, if you are obeying rules, traffic lights are going to turn green as you're moving. And you can imagine yourself as the data moving down the Franklin Street in San Francisco. And if you're moving at whatever the speed limit there is, 40 miles per hour or something like that, if you're moving at 40 miles per hour, you're going to see the green wave in front of you. If you're going 50 miles per hour, what's going to happen? You're going too fast, you'll make it for one or two latches, and then you have to brake and wait because you are about to race to the traffic lights. You're not supposed to do that. What happens if you're driving too slow? If you're driving 20 miles per hour? Again, this is not a system that is really designed for you, but again, you will make it for a few of them, and you'll have to wait again. But we can accommodate those super long paths there as well. There is something that I'm going to refer to in a second. But this is basically a system that is designed for paths that are moving at 40 miles per hour down the Franklin Street, and the green lights are just going to happen. If you're a short path, if you're too fast, you got to wait. And that's okay. But you don't want the long paths to wait. So ideally, data would arrive to a transparent latch. Go to the opposite phase, transparent latch, and again, hit the transparent latch. If everything is perfect, if the logic is perfectly partitioned between the clock phases, it would clear the first latch. At the same time, same phase of the clock, as it will arrive to the next latch of the same phase. So the amount of logic that is in between these two events corresponds to CLH plus CLL plus 2 D2Q delays. And that should match exactly the clock cycle. Okay. Now, you see that we have some forgiveness over here. The clock cycle doesn't, the logic does not necessarily have to fit the clock cycle, and does not have to be evenly divided between the high and low clock periods. We have ability to move things around. So we can borrow time between the high and low phase, meaning the CLH can be longer than CLL. Does not have to be perfectly divided, but should add up to the same clock cycle. But also, if we exceed the sum of the two, can exceed the clock period. What happens then? If it exceeds the clock period, if we have a slower car going through Franklin Street, you're clearing two lights a little bit slower than going at 35 miles per hour. In order to stay on pace, what do you need to do with the next two traffic lights? You go faster, meaning you can borrow time or steal time, depends how they say. You can use a little more time in the first pipeline stage and then pay it back later on. You'll find this kind of a timing, this kind of a borrowing frequently applied around register files in microprocessors because they're slow. And they'll try to borrow time for that. The story of hold times here is similar. We can vary the amount of logic that we can have between the CLH and CLL, but we have to observe the hold times, right? The hold time here is associated with the sampling edge of the latch, and we just have to make sure to observe that none of these paths ever hits the whole time of the latch. I'm not going to dive into this, but it is simply CU plus hold time has to be longer than the worst case Sp22 plus CLL. We can work that. They do want to spend a little bit of a time on this idea of slack passing and time borrowing, because it gets really hairy. I mean, Franklin Street has like 40 traffic lights or something like that. So trying to, how many possible timing paths are out there? I mean, a car can start at any of the green lights down the Franklin Street and exit any of them. So we need to time very large number of them. I mean, I would have to time it between not just a pair of flip-flops, which is what we've done in an edge-based system. I have to do it for every pair of latches. It gets really tricky. By the way, I mean, timing tools that Synopsys and Cadence do that right, but they ask you to write the constraints for every single pair. You will get exhausted pretty quickly if you do that for like a 40-stage pipeline or 20-stage pipeline. And the likelihood of an error will be high. We try to break that process up in something that is more manageable. How do we do that? We essentially try to analyze it per cycle or even per half cycle. We say that we expect the CLH to be evaluated during the half clock cycle and CLL to be evaluated during the other low period of the other half of a clock cycle. And we just measure it, how much of a logic do we have compared to the half of a clock period, or the sum of two compared to the whole clock. And if our logic delay is longer than the cycle time for that particular period, what does that mean? It means that we have borrowed time or stolen some of the time. If we use less time than we are allotted, what does it mean? That we have saved some time and we have some slack and we can pass that slack to the next stage. So the illustration that I've had, if you start in exactly the same time, same phase within the clock period, then you're perfectly utilizing this time. You just have to make sure that you're always arriving to a transparent latch and everything is going to be good. But it can happen that you can start evaluating earlier if the previous stage has saved some time. In other words, it has passed the slack to your stage. The other option here is if you start evaluating later, for example, in here, or you took a little bit longer time during one phase of a clock, that means that you borrowed time from the next stage. If you borrow time, so it looks really convenient. How much time can you borrow in a two-phase system? And everything's still, not running the whole time or part time or set the time. How much time can you borrow in a two-phase launch-based system? You can borrow, if you look at it, essentially, I can push this down, or this evaluation down by about a half of a clock cycle, almost a whole half of a clock cycle. So between a pair of same phase latches, I can fit about 1.5 worth of cycle times worth of logic. Can I just keep doing that? That would violate some timing very, very quickly. But do I have, if I borrow that half of one cycle, do I have to pay it back immediately? No, as long as I keep running into transparent latches, I can pay that back at the very end of the pipeline and have the last stage be only worth a half of a cycle time of logic. So you can have 1.5 cycles times of logic with 1.5 in the very end. Or whenever I have a memory access, I can play with the timing to stretch the cycle to have more time for memory access. Or in interfaces, very commonly, you're looking at things like DDR and so on, but the timing, really high speed serial, that's exactly what they basically squeeze that, stretch that time. All of your high speed serial friends in DWRC, that's what they're doing. They won't. Just on like basically playing with 2 cycles because that's all what they have in there. Stretch one, shrink the other one. Make sense? Now, the timing here, timing analysis goes like that, right? I mean, you have up to 1.5 clock cycles. And all what you need to do is to make sure that you're accounting for that properly. If you're starting earlier than you're supposed to, somebody has passed this time, pass on slack to you. And if you're ending later than when you're supposed to, you're borrowing time from someone else. In general, here is where you're supposed to start and where you're supposed to end. Any time that stretches out of that is borrowed or passed. And again, this can get really hairy. The way how you do this in timing analysis tools is you have to write clock constraints for every pair of sources and sinks. People don't like to do that, although you can gain stuff from that, and as a result, 99.99 something of timing in digital systems is edge-based. Only when things are critical, you may be willing to go to latch-based, and there is no other option like high-speed serial. Okay, any questions about this? Yes.
What do you mean when you say it's critical you have to resort to latch-based?
If the timing, if there is no other way if you have to fit logic, you have some set cycle time goal.
Flexibility.
No, you have a product that you have to ship at 4 gigahertz, and there is like just no way to fit to one pipeline stage to make it complete in 250 picoseconds. It's a 320 picosecond memory path. So what do? You borrow time by using latches or do some other manipulation of a clock to stretch one pipeline stage and then pay it back afterwards.
And it's because of this flexibility of borrowing time.
Correct.
That we choose latch-based systems.
Yes.
Okay.
The other option is to manipulate the clock. For that is hairier, that is harder in general. Similarly, if you're looking at many of these, 100 to 200 gigabit per second serial links, you have like 5 picoseconds to do something, and you usually can't do that. You need like 7, so you borrow a few from somewhere else. In the end, that has to be resynchronized to some main clock, and that's where you pay things back. Okay, we have an assignment one due tomorrow. Therefore, we have a quiz always after the assignment. The quiz covers first 10 lectures that this assignment covered. So there will be a quiz next lecture on Tuesday. And we have a lab that is due next week. Eric will continue developing a little bit of these training materials, but they're not going to be formally assigned. So it's the project time. Let's take a look quickly at the latch design. And I will link this on the board. Okay, how do I build a two-input multiplexer? So multiplexer based on the select signal will assign either the value of A to the output Y if select is equal to 1, or B if select is equal to 0. There are two ways to build that. One that is kind of a natural is to imagine here is by using transmission gate multiplexers. So you can pick this side. If select is equal to 1, A bar will go 2. If select is equal to 0, B bar will go to the output. The other way to do that is by using straight CMOS logic. We can get this out of straight of a truth table, for example, or sometimes we'll call this a C-square MOS or stacked CMOS, where the select signal, if it is equal to 1, will pass Y to the output, and then you would see this as a wired OR that would pass a B to the output if select is equal to low. What's the difference between the C-square MOS? And what's faster, a C-square MOS or a transmission gate? Anybody has an opinion on that? In standard cell libraries, you'll find a mix of C-square MOS and transmission gates, indicating that they may be about the same. Can somebody convince me quickly why they're about the same? If I do this, if I put a wire between these two, what do I get? Is this the same thing? So what's the difference between the two? I mean, one wire. What does that wire change in terms of sizing? I'll have to come to that in the next lecture, and I'll have a little different strategy with using the screens. But anyway, the next lecture is in person because we do have a quiz here, one of the 4 quizzes. So I'll pause here. We'll go over it next time. You still should get your project feedback like today, and you need to get going with that too. With the midterm write-ups. Any questions? My office hour is going to be in my office because it's raining outside. My office and Zoom, if you have any questions.
Professor, how long was it? Quick.
15 minutes at the end of the lecture.